Okay, so we'll see few examples in limit continuity and differentiability for 3D. Okay, so we have already talked about limit continuity and differentiability is a kind of detailed fashion. So if I have a kind of a graph equation, uh, okay, so this is my a new graph, and then okay, so if this is xy plane, then there is a graph over it, and the idea is to continue to calculate the limit continuity and differentiability on the kind of xy plane where there is any point called a comma b. So if this is xy plane, then there is any point a comma b. At this point, if we have function fxy and then we place the limit on xy when it is limiting to a comma b, xy is approaching. So xy is anywhere on this plane and this is a comma b. If from xy we approach near a comma b and there is infinitesimal small distance between a comma b and xy, at that point if I limit the function fxy where xy tends to a comma b, then fxy should also limit to function a comma b. So that is limiting. If that is the case, then it is continuous at point A and B. So the graph is continuous at point A, comma B. So this is what we have been seeing all along. So that is the scenario. Now question arises that from which direction x and y should arrive at a comma b. If it is 2D or line equation, then certainly it would only arrive from minus x-axis or plus axis because independent variable is only one, that is x, and we are talking about it arriving at only single point, that is a. Now, when we talk about the 3D, where we have two independent variables x and y, in that case, on the surface a comma b point, xy would approach to a comma b from 360 degree, from infinite direction. 360 degree is not only 360 integral value. 360 degree means between 1 2 degrees there will be infinite angles. So 1D, I mean single line or 2D, there it is two direction, plus x or minus x or one direction. But in 3D it is infinite. Only in surface I am talking about it is infinite. If we go for actual 3D, then again infinite means from all three direction it will come. Here from two directions, x and y would approach to a comma. Now, when it is approaching, then we calculate the limit, and if limit exists, we consider this is continuous. Now we calculate, we also see that it is partial derivative at a comma b in direction of x and y. If that is the case, then the limit for a tangential surface, if there is a model, okay, if there is a model, and inside the model there is a point, inside the model there is a point, okay, at that point, so model has a point, at that point it meets, or it meets a point on tangential surface, so there it meets. Now the flat one is tangential surface and this is the actual graph or model. Now if two equation if we know, then the point at which it meets, there is no difference between them, otherwise it goes round and it goes in this direction. So there is a gap started coming between the tangential surface and the actual model. So that is the scenario. In that case we consider the gap that starts. So at point A comma B, they are the same. But beyond A comma B, tangential surface takes another direction, and sphere, what we are seeing now, it takes another direction. So there is a gap that comes in between. That gap, we address it as an error. So now we calculate, earlier we were calculating fxy limiting to a comma b, or fab xy limiting to a comma b. Now we will talk about the error, the gap what we are seeing, that should be limiting to a comma b. The error should be limiting to the a where it meets. So when it is limiting, when, if I consider there it is limiting, so the at any point it is x and y. So x y, when it limit to a comma b, then error tends to 0. Whereas in continuity, the fxy tends to fab when x comma y tends to a comma b. Here, if x comma y tends to a comma b, then error tends to 0. So error is nothing but the graph of the model fxy minus lxy. Lxy is the tangential surface. So if I subtract and if I divide it by the distance between a comma b and x and y. Suppose the distance is h and k. So a comma b and any x and y. So if I have, okay, so if I have a sphere, if I have a tangential surface, and if I have a sphere, then oh, okay, so we can see the gap, my kind of finger that is moving. So we can see the gap. This gap is slowly, it is decreasing when it is going to point a comma b, or here a, when they meet a comma b. So that error should be, that error should be 0, where we limit any point around the a comma b, any point around a comma b. If this is a comma b, any point around a comma b is x and y, the error at x and y, okay, should be 0 when x and y tends to a comma b. So that is the equation. Error x and y, if I see the relative error, then okay, so or I can say normalized error or differential error rather. So if I talk about differential error, that is fxy minus lxy divided by the distance between x and xy and a comma b. That is h square plus k square square root, or delta x square plus delta y square, where if we see the variation in delta x and delta y, then xy would approach to a comma b from all the directions. Okay, so if this is a comma b, okay, and if delta y is 0 and delta x has some value, then we are talking about moving from the x direction to the a comma b. If delta x is 0 and delta y has value, we are talking about moving from y direction to 0. If delta x and delta y has some variation, then we are talking about moving from all direction at as the relative value of delta x and delta y along a comma b. So delta x and delta y we are referring as h and k. If that is the case, then exy equal to, sorry, e a plus h, error at any point. Okay, first I'll do xy. So error at any point xy equal to fxy minus lxy divided by delta x square plus delta y square square root. This is the differential error we can say. Now, if it is at distance h and k from the a comma b, I can say error a plus h b plus k equal to f a plus h b plus k minus l a plus h b plus k divided by h square plus k square square. Okay, so this way, if the limit what we are talking about, where h and k tends to 0, or a plus h b plus k, or x and y tends to a comma b, then this differential error, that limit tends to 0. If that is the case, then it is differentiable. So we are talking about limit continuity and differentiability. So if limit exists, we check first if limit exists. If limit exists, then it is continuous. If it is continuous and partial derivative also exists, then we come up with the tangential surface, and difference between the sphere, the graph of the sphere, graph equation, and tangential surface divided by the distance of the x and y from the a comma b. And if we limit the x and y to the a comma b, then fxy minus lxy divided by the distance, that is h square plus k square square root, that is the differential error, that limit should tends to 0. If that is the case, then it is differentiable. So if it is continuity, continuity is there at point a comma b, and partial derivative exists, and then the limit between the graph equation and tangential surface where x and y tends to a comma b, that error is 0, then it is differentiable. Next, we talked about partial derivative continuity. Leave everything, whatever the Bible we talked about, okay, whatever the story we talked about, whatever the concept we talked about, okay, just get it aside, and now think about that only partial derivative. If we know the kind of if we know the partial derivative, if we know the partial derivative, then if it partial derivative are continuous in both directions, okay, if partial derivative are continuous in both direction x and y, then it is considered as continuity, means partial derivative, they come in equation of x and y. And then if they are continuous, partial derivative both uh, dz by dx and dz by dy in a particular domain or in a particular region. So for that full region, it should be considered as continuous, as differentiable. Okay. Now we'll go with the, so we start with the concept that it should be continuity, it should continue, means there should be continuity, and partial derivative exists, then only we can proceed. This is the first thing that we talked. Second thing, we talked about the continuity in the partial derivative. Two way we prove that it is differentiable. Now first we will see that is continuity and both partial derivative exist. So now we will take a case where partial derivative do not exist, like cone. Okay, so I'll make a cone. Okay, this is really a cone. You can see it is a cone, and this is the bottom part of the cone. This is a cone, and this is the cone, and this is bottom part of the cone. So this sits at origin, and this is the cone. If we see kind of the vertical area, cross section in the vertical area, that is also called contour. So if you see the contour, then it is circle, bigger circle, a smaller circle, and here it is a point. Now at this point, we'll calculate the, if it is, if a partial derivative exists or not. But if you see from this direction, if slope is positive, then this direction, the slope, one direction slope is positive, the partial derivative means slope, and then other direction slope is negative, other way. And here we'll see what is the scenario, because it is not a paraboloid. If it is paraboloid, then it will be like this, then the derivative will be 0 here. It is a sharp point here, okay, and then this direction, y direction also will see, x direction also will see. That partial derivative. Now the equation for the circle, if I see, then it will be x square plus y square square root. So the equation of the cone is z equal to x square plus y square square. Now with the kind of various x and y, we get the height. If x and y are more, because it's a cone, right? So if from center, at center 0 0, there is no height. But if we go along, then this radius also increases and height also increases. Same. So if I go along, so if this is the cone, then here it is centered. But if I go in x direction and y direction more, then radius also increases, height also increases. This is what we are saying. So z equal to, or fxy equal to x square plus y square square root, that would be the perfect equation. If that is the case, now we will calculate that dz by dx. So dz by dx. So in x direction, two ways we can calculate. One is the dfx by dx, that is partial derivative along x-axis. Okay, that is equal to fx plus delta xy minus fxy divided by delta x, because in y direction there is no movement. So and y is fixed. So f x plus delta x y minus fxy by delta x. Now we are calculating at point a comma b, that is 0, and at a distance h, instead of delta x we call it h. So f a plus h b, f a b by h. So a and b are 0. So f h 0, fh comma 0 minus f 0 0 divided by h. Now fh0, x square plus y square square root, that will come as a square root of h divided by h. So square root of h, square root of h square would be kind of the absolute value, that is plus minus h by h. So plus minus 1. Okay, plus minus 1 in the sense that partial derivative, if, okay, if this is x axis and this is center, at center, okay, in x direction it is plus 1, and at center in minus x direction it is minus 1. So from minus 1 it is coming like this, at center sharply it is coming here, then so this is not limited. Okay, when we talk about limiting, what is limitable? So limit exists when from the point where we are calculating the limit, there should be smooth transition as per the variation in the h. If the partial derivative they vary along with h, or they have some a constant value along it, like it is 1, okay, it starts from 1 and it is 1, then also it's all right. But here it is discontinuity, means it is coming as 1, suddenly making sharp change and coming. So both direction partial derivative varies. So this is considered as it is not limitable. If that is the case, then it is not, partial derivative do not exist. If that is the case, if I calculate fy dz by dy, then it will also come as plus minus 1. Then partial derivative for the cone at the bottom, if this is the cone, then at the bottom, that point partial derivative do not exist. Okay, I can calculate the pure differentiation also, dz by dx, where x square plus y square. So that will come as, a 2x half, that will come as x by a square root of x square by y square. So at h, if I consider k equal to 0 and h, then it will come as h by plus minus h, that is plus minus 1, same. Okay, so if partial derivative is coming as plus minus 1, From one side it is plus. That's why I was saying if it is a cone, then this direction, if there is a partial derivative and its value is a, then partial derivative along this side is minus b because they are opposite to each other. And they meet at this point. So at that point, the partial derivative has no continuity. There is no limit because it is sharply it is changing the direction. So it is a kind of, it's not zero. If partial derivative can be zero, if partial derivative zero, then that is the case of maxima and minima. So there partial derivative exists, but here plus minus 1 means in both direction, okay, just slightly in right direction it is plus 1, left direction the rate of change sharply it alters its value. So it is not limitable. So in that case partial derivative do not exist. We can move ahead calculating the for the differentiability also, that is error. So error, when error tends, limit of the error tends to 0, then differentiability, the differentiability concern what we are saying, so that is differentiable if it tends to 0. So that is the case. So here we can calculate, we are not running away. So we will calculate the error condition if it is limit is 0. Now if error at a plus h b plus, anyway partial derivative did not happen. Now, if partial derivative does not happen, we will not calculate the continuity. We will directly see if it is differentiable or not. If that is the case, then now we will see that what is the error limit. So, f error a plus h b plus k equal to f a plus h b plus k minus l a plus h b plus k divided by h square plus k square square. Now, where a comma b is 0, okay, then it will come fx f a plus h b plus k will come as h square plus k square square minus lxy. So lxy, okay, so for lxy we have fab. So fab is 0 plus mx minus a. So that will come as mh plus ny minus b. So that will come as nk. So that whole it will come at h square plus k square square root minus mh minus nk divided by x square plus y square square. Now there are two paths that we can take. So error at a plus h b plus k, at that position the error where h and k tends to 0. At that position, the error is f a plus h b plus k minus f l a plus h b plus k divided by h square plus k square square. So f a plus h b plus k is a plus h l square b plus h k b plus a plus h l a plus h whole square plus b plus k whole square square root. That is the equation of fxy minus FAB. So at AB minus FAB minus M x minus a minus n y minus b divided by h square plus k square square root. Okay. So error at any point x and y equal to the graph value fxy minus tangential surface value lxy divided by the distance, that is delta x square plus delta y square square root, where delta x is x minus a and delta y is y minus b at point a comma b. So if x is delta x away from a or h and k away from a and b, then we are trying to calculate error at a plus h b plus k. Straightforward, equal to fxy. Now xy is a plus h, y x and y is b plus k. So f a plus h b plus k minus l a plus h b plus k divided by h square plus k square square root. So then it comes as, if a comma b is 0, then h square plus k square, that is f xy minus lxy, then lxy is nothing but FAB plus M x minus A plus N y minus B. Okay, if that is the case, then it would come as, okay, if that is the case, then FAB is 0, because FAB is A square plus B square root, that is the cone equation. So 0 plus M x minus A, x is A plus H, so that will come as MH plus NK. So it will come as H square plus K square root minus MH minus NK divided by H square plus K square. Now, if I divide it, it will come as 1 minus MH minus 1 H square plus K square divided by H square plus K square, it will come as 1. So 1 minus MH, 1 minus MH, okay, divided by H square plus K square minus N K divided by H square plus K square. There are two paths. One path we will consider K as 0. If K is 0, then, sorry, HK, yeah, K is 0. If that is the case, then it will come as 1 minus M, okay, 1 minus MH divided by 1 minus 1 minus MH divided by plus minus H, because the square root of H square is plus minus H. Okay, so this is also not limitable. Now, for limit to happen, M should be 0. M is not 0. dz by dx, we calculated it is plus minus 1. So at any what we are learning now, if there is an extremity, like if there is a cone, and at this point there is an extreme point, this is called extrema. At this point, the partial derivative must be defined, and typically it should be 0 rather than plus minus 1. So differentiability also it is not continuous. It comes as 1 minus m h by plus minus h. Okay, so this differentiability to exist, where the m h by h, it should be 0. If I leave this one side, okay, constant 1 minus m h by plus minus h, the one part that is constant, if I in differentiability, if I leave this, then it will come as minus m h by plus minus 1. So this has to be 0, then m should be 0, where m is the partial derivative along x-axis, that is not 0, that is plus minus 1. So this cannot become 0, it is not differentiable either. Okay, I think it is getting complex. So, we'll proceed on this. Idea was to finish this. So, we have taken a case where the partial derivative along x-axis, partial derivative along y-axis, both do not exist. If they do not exist, okay, if they do not exist, then the derivative differentiability would also not exist, because we saw the differentiability directly proportional to m. What is the condition? It should be 0, then only it will become 0. Yeah. Okay, before we end, can we calculate continuity also? Means it's not, I believe it should be okay. So to calculate the continuity, we have fxy equal to x square plus y square square root. Now for any h and k, or delta x delta y, from point A comma B, okay, from A comma B, there is another point called h and k. There is another point called something which is at distance from A comma B, AH and K. Okay, if this is A comma B, then there is any point here that is at distance h in x direction and distance k in y direction. If that is the case, then we are at another point, that is A plus h and B plus k. That is, so that is any point x comma y. Continuity means if I approach this A comma B from any direction x y, okay, limit should be there, it should be limitable. Means x and y tends to A comma B, then fxy tends to fab. That is the scenario. There should not be sharp change anywhere to be it kind of continuous. Now we calculate. So if x and y, if fxy x square plus y square square root, that is the equation of the cone, then at any point a plus h b plus k, that is a plus h whole square plus b plus k whole square square root. Now if I consider at a comma b as 0, then it will come as h square plus k square square.